Everything you see in the night sky is a tiny fraction of reality. The stars, the galaxies, the glowing cosmic clouds, they represent less than 5% of the universe. The rest is a profound and invisible mystery, a cosmos of hidden particles that hold the true secrets of existence. By the end of this, you will journey through 30 of the most incredible theories that explain this missing universe, from ghostly matter that passes through you every second to entities that might exist in extra dimensions. We are assembling a puzzle where 95% of the pieces are missing, and the remaining fragments suggest a reality far stranger than we ever dreamed. What do you believe is the universe's biggest secret? The hunt for this missing cosmos begins with a single, dominant idea. For decades, the leading suspect has been a particle so elusive it could pass through a light year of solid lead without a trace. They are called WIMP, or weakly interacting massive particles. The name tells you almost everything you need to know. They are believed to be massive, meaning they have significant weight, far heavier than a proton. And they are weakly interacting, which means they ignore almost every force in the universe except two. They feel gravity, which is how they sculpt galaxies and hold clusters together. And they might occasionally bump into normal matter through the weak nuclear force, the same subtle force behind certain types of radioactivity. But that interaction is so incredibly rare, it's like trying to hear a single whisper in a roaring hurricane. This is why we have never seen one directly. To find them, scientists have built the quietest rooms in the universe, laboratories buried deep underground, beneath mountains or in old mines, shielded from cosmic rays and everyday radiation. Experiments like ELUX and XENO use vast vats of ultra-pure liquid xenon, waiting in the dark and the cold for the impossible to happen, for a WIMP to strike a single atom and create a tiny flash of light or a minute electrical signal. They have been waiting for years, and so far the detectors have seen nothing. The silence is growing louder. This great non-discovery points to a deeper mystery. Why do we believe in WIMPs so strongly? Part of their appeal is an elegant cosmic coincidence. Calculations show that if such particles were left over from the Big Bang, their leftover abundance today would naturally match the amount of dark matter we observe. It is a beautiful piece of theoretical math. Furthermore, WIMP are a favorite child of a grander idea called supersymmetry. This theory proposes that every known particle has a hidden, heavier twin. The lightest of these supersymmetric particles could be stable, invisible, and floating around everywhere, perfectly fitting the description of a WIMP. It is a compelling story, one that has guided physics for a generation. Yet the universe has not cooperated. The detectors remain empty, and supersymmetry has not appeared in our most powerful particle colliders. The leading candidate is starting to look like a ghost that may not exist at all, forcing us to look elsewhere in our catalog of cosmic suspects. The silence of those underground detectors has forced physicists to consider a radically different kind of ghost. What if dark matter is not made of heavy, sluggish particles, but of something incredibly light and fast, more like a cosmic breeze than a hidden rock? This is the world of axions. While WIMP are the burly, strong and silent type, axions are the wispy, ethereal alternative, born from solving a different and equally profound mystery in physics. Our story begins not with missing mass, but with a symmetry that should be broken but is not. Inside every proton and neutron, quarks are held together by the strong nuclear force, governed by a theory called quantum chromodynamics. This theory has a puzzling feature. Its equations allow for a certain kind of asymmetry, a difference in how particles and their mirror images behave under the combination of charge and parity. This is called the strong CP problem. In simple terms, the math says the neutron should have a much stronger electric dipole moment, a sort of internal charge imbalance, making it wobble in an electric field. Yet when measured, the neutron is perfectly symmetrical, as if this asymmetry does not exist at all. Why does nature respect this symmetry when the rules say it does not have to? In the 1970s, physicists Roberto Pexi and Helen Quinn proposed an elegant fix. They suggested a new, fundamental symmetry that, when broken, would naturally cancel out this problematic asymmetry. And whenever a symmetry breaks in quantum field theory, a new particle is born. That particle is the action. It is a cosmic byproduct of making the neutron perfectly round. So from its very conception, the action solves a deep puzzle in the heart of matter itself. But then, a beautiful coincidence emerged. When theorists calculated the properties of this new particle, they found it would be incredibly light, potentially billions of times lighter than an electron, and extraordinarily numerous. It would barely interact with normal matter, flitting through the universe in vast, wave-like clouds. And if it had just the right mass, its collective gravity could account for all the dark matter we observe. One elegant idea solved two monumental problems at once. Hunting for an action is a completely different game than hunting for a WIMP. You do not wait for it to bump into an atom. Instead, you try to convince it to transform. In the presence of a tremendously strong magnetic field, theory predicts that an action could spontaneously convert into a faint microwave photon. The search, then, is like tuning a cosmic radio to a frequency no one has ever heard. This is the goal of experiments like the Action Dark Matter experiment or ADMX. It uses a powerful superconducting magnet and an ultra-sensitive microwave receiver inside a resonant cavity. Scientists slowly tune the cavity, changing its size, scanning through millions of possible frequencies one by one, listening for the faint whisper of an action turning into a photon. It is a painstaking search for a needle in a universe-sized haystack, but it represents a brilliant end run around the silent WIMP detectors. The action is a testament to the beauty of theoretical physics, where solving one mystery might accidentally reveal the answer to another. But what if dark matter is not a single particle at all, but something far more alien and complex? The search for an action is a delicate act of cosmic listening, but what if the truth is even more elusive? What if the dark matter particle is not something new we have to invent, but a hidden version of a ghost we already know? Meet the sterile neutrino, a ghostlier ghost. We are already surrounded by trillions of neutrinos every second, streaming from the sun, from distant supernova, and from the Big Bang itself. These ordinary neutrinos are famously aloof, passing through our planet as if it were empty space. But they do have one tiny connection to our world, the weak nuclear force. It is an incredibly faint touch, but it is enough for us to detect them in vast underground tanks filled with cleaning fluid or heavy water. Now imagine a neutrino that has given up even that one tenuous link. A particle that feels only gravity and nothing else. That is the sterile neutrino. It is called sterile because it is completely inert to all the fundamental forces except gravity. It would be the ultimate cosmic spectator, a particle that watches the universe unfold without ever participating. The theory suggests these sterile neutrinos could be born from a quantum dance with their ordinary cousins. The three known types of neutrinos, electron, muon, and tau, are known to oscillate or morph from one flavor into another as they travel. This proves they have a tiny amount of mass. The sterile neutrino idea proposes that sometimes during this oscillation, a regular neutrino briefly transforms into this sterile, invisible state before changing back. If that sterile state has mass, then these fleeting moments of invisibility could add up to a significant gravitational footprint across the cosmos. They could account for a portion or even all of the dark matter. Intriguingly, this idea is not just mathematical speculation. It might explain stubborn anomalies in real data. Several neutrino detection experiments, like the liquid scintillator neutrino detector and later mini BUNI, have recorded more neutrino events than their models predict. One possible explanation is that some of the neutrinos are oscillating into these sterile, undetectable forms and then back again, subtly skewing the counts. It is a discrepancy that has haunted physicists for years, a tiny crack in the standard model where a shadow universe might be leaking through. The implications go even deeper than dark matter. Sterile neutrinos could be a key player in the universe's original sin, the matter-antimatter asymmetry. In the first hot moments after the Big Bang, sterile neutrinos could have decayed asymmetrically, producing slightly more matter particles than antimatter particles. Over time, as matter and antimatter annihilated each other, that tiny excess would be all that remained, eventually forming every star, planet, and person we see today. In this view, sterile neutrinos are not just hidden mass, they are the reason anything exists at all. So while we build vast machines to listen for new particles, the answer might be hiding in plain sight, in the subtle misbehavior of the ghosts we thought we knew. But the universe's hidden inventory is not limited to strange new particles. Before WIMP and axions dominated the conversation, scientists looked for the missing mass in a more familiar form, ordinary matter that simply did not shine. This was the theory of MACHO, or massive astrophysical compact halo objects. The idea was beautifully simple. What if dark matter is not dark at all, but just dim? Picture the vast halo of our galaxy. Could it be filled with countless failed stars, rogue planets, or the cold, dark remnants of dead stars? Brown dwarfs, objects too small to ignite hydrogen fusion, would glow only faintly in infrared. Ancient neutron stars and stellar mass black holes, the cold cinders of supernova, would be completely invisible. If enough of these objects littered the galactic outskirts, their collective gravity could explain the rotation curves of galaxies without any new physics. It was an elegant and conservative solution, using the known building blocks of the cosmos to solve its greatest mystery. To test this, astronomers turned to a cosmic trick called gravitational microlensing. Imagine a distant star in a neighboring galaxy like the Large Magellanic Cloud. Now imagine a MACHO, a dark compact object in our galaxy's halo, drifting silently through space. If it passes directly between us and that background star, its gravity will act as a tiny lens, bending and focusing the star's light. For a brief period, the background star will appear to brighten, then fade in a perfectly symmetric curve. By monitoring millions of stars for these telltale flashes, surveys like the MACHO project and EROS could count the invisible population. They watched for years, cataloging a handful of events. The result was definitive yet disappointing. These dark, compact objects do exist, but there are not nearly enough of them. MACHO might make up at most a few % of the dark matter halo. A primary component of the universe's missing mass could not be ordinary baryonic matter. It had to be something truly exotic, yet, like a good mystery, one door closed only for another to crack open. While stellar remnants were ruled out, a far more ancient and enigmatic possibility resurfaced: primordial black holes. These are not the black holes born from dying stars. They are thought to be fossils from the universe's first violent second, forged in the extreme densities of the Big Bang itself. They could be any size, from as small as an asteroid to many times the mass of our Sun. For decades, they were considered a fringe idea, but recent observations have brought them back into the light. The detection of gravitational waves from merging black holes by LIGO revealed pairs with masses that were surprisingly large and puzzlingly similar. Some theorists suggest these could be primordial black holes that have wandered together since the dawn of time. Furthermore, careful studies of the cosmic microwave background and the distribution of galaxies place limits on how much dark matter could be in the form of compact objects. The current consensus is that primordial black holes cannot be all of the dark matter, but they could certainly be a portion of it, perhaps even a significant one. So, while MACHO failed as a complete answer, they left behind a tantalizing legacy, a reminder that the dark universe might still harbor ancient monsters from the very beginning of everything. These ancient black holes are not born from dead stars. They are relics of creation itself, formed in the chaotic furnace of the universe's first fraction of a second. This is the theory of primordial black holes. Picture the cosmos not even a second old, an unimaginably dense and hot soup of energy. Within that roiling plasma, random quantum fluctuations could have created tiny, dense knots. If one of these knots was dense enough, its own gravity would have caused it to collapse directly into a black hole, bypassing the need for a star entirely. These primordial black holes could have formed with almost any mass, from something as light as a small asteroid to objects thousands of times heavier than our Sun. They would have been scattered across the infant universe like seeds, and their sheer gravitational pull could, in theory, account for all the dark matter we observe today. For decades, this idea was on the fringe, considered an interesting but unlikely possibility. Then, in 2015, the LIGO Observatory heard its first gravitational wave chirp, the sound of two black holes merging. The signal was shocking. The black holes were each about 30 times the mass of the Sun, far heavier than the stellar mass black holes astronomers were used to. More puzzling, they were in a region of space where we would not expect to find many large stars to create them. Could these be primordial black holes, ancient relics that have been drifting together since the dawn of time? The LIGO detections have since revealed several more mergers with similar, surprisingly large masses, reigniting serious interest in this decades-old theory. But if they are everywhere, constituting the dark matter halos of galaxies, how do we find something that emits no light? Astronomers hunt for them using their shadow. Just as with Macho, they use gravitational microlensing, watching for stars that briefly brighten as a dark object passes in front. But to scan for the full range of possible primordial black holes, from asteroid size to solar mass, requires a vast and constant vigil. Projects like the Optical Gravitational Lensing Experiment, or OGLE, and the upcoming Nancy Grace Roman Space Telescope are designed to monitor hundreds of millions of stars, searching for these fleeting winks in the night. Another method looks at the echo of the Big Bang itself, the cosmic microwave background. If a swarm of primordial black holes existed in the early universe, they would have absorbed and re-emitted radiation, creating subtle temperature distortions in this ancient light. So far, precise measurements from satellites like Planck have found no such signal, which rules out primordial black holes being all of the dark matter across a wide range of masses. Yet, there remain intriguing windows, particularly for black holes with masses similar to a large asteroid, or, at the other extreme, many times that of our Sun, where they could still be a major component. And then there is the strangest fate of the smallest ones. According to Stephen Hawking's famous theory, black holes are not completely black. They slowly evaporate, losing mass by emitting a faint glow of particles now called Hawking radiation. For a stellar mass black hole, this process is immeasurably slow, taking far longer than the current age of the universe. But a tiny asteroid mass primordial black hole, formed in that first violent second, would be nearing the end of its life about now. Its evaporation would be a spectacular final act, ending in a burst of high-energy gamma rays. Astronomers scan the skies for these unexplained gamma-ray flashes, a potential final signature of a dark matter particle dying in a blaze of glory. The search for primordial black holes is a hunt for the universe's first structures, fossils that could rewrite the story of both dark matter and cosmic dawn. The universe's hidden architects might not be solitary ghosts, but a society with its own rules. This brings us to SIMP, or strongly interacting massive particles. While their name sounds similar to WIMP, their proposed nature is a dramatic shift. A WIMP is a lone wanderer, barely acknowledging anything else in the cosmos. A SIMP, however, is a social particle. The theory suggests these particles interact powerfully with each other, through their own unknown dark force, while remaining almost completely aloof from the ordinary matter that makes up our world. Imagine two crowds passing through each other in a grand station. One crowd is us, made of light and atoms. The other is the dark matter, made of simp. People in our crowd do not feel or see the other at all. But within that dark crowd, individuals are constantly bumping into each other, chatting, exchanging energy, forming a fluid and interactive society all their own. This simple idea of self-interaction could solve one of the most stubborn puzzles in modern cosmology, known as the cusp core problem. Computer simulations that model the universe with standard, non-interacting dark matter like WIMP predict a specific shape for galaxies. They suggest that dark matter should pile up densely at the very center of a galaxy's halo, creating a sharp peak or cusp of incredible density. But when astronomers observe real dwarf galaxies, the smallest and most dark matter-dominated systems, they find something different. The centers of these galaxies appear much smoother and flatter. They have a core, not a cusp. It is as if some cosmic pressure has pushed the dark matter away from the very center, preventing that sharp spike. Non-interacting particles would naturally sink to the middle, but particles that constantly scatter off one another would behave more like a fluid or a gas. They would resist being compressed into such a dense knot, naturally smoothing out the center into a soft core. This is the elegant promise of SIM. Their strong mutual interactions provide that internal pressure, offering a neat explanation for why small galaxies look the way they do. Detecting such a particle, however, presents a unique challenge. Since they ignore normal matter almost entirely, our underground detectors would remain silent. Their signature must be sought on a galactic scale. One of the most promising places to look is in the aftermath of cosmic collisions. When two gigantic clusters of galaxies slam into each other, it is the most energetic event since the Big Bang. The ordinary matter in these clusters, mostly hot gas, experiences friction and drag. It slows down and gets stuck in the middle of the collision, but dark matter, which does not feel electromagnetic forces, should simply sail right through. Astronomers can map the dark matter in such collisions by using gravitational lensing, watching how the cluster's mass bends the light from galaxies behind it. In several famous collisions, like the Bullet cluster, the dark matter maps did indeed show the mass separating from the hot gas, exactly as predicted. But if dark matter is made of simp, which interact with each other, a subtle difference should appear. Even though they ignore normal matter, the simp within one cluster would scatter off the simp in the other cluster during the collision. This would create a slight drag, causing the dark matter to lag behind its predicted path or to spread out more than expected. By meticulously analyzing the distribution of mass in these colossal wreckage fields, astronomers are looking for that telltale smear, the ghostly fingerprint of dark matter interacting with itself. It is a search for a shadow of a shadow, a hint of structure within the invisible majority. While SIMP propose a hidden society, another theory reaches for an ultimate cosmic unity. Deep within the equations of supergravity, a theory that attempts to marry supersymmetry with Einstein's relativity, lies a hypothetical particle of profound significance, the gravitino. To understand it, we must first meet its ordinary sibling, the graviton. The graviton is the proposed force-carrying particle for gravity, a tiny packet of gravitational energy, though it has never been detected. According to supersymmetry, every particle has a superpartner. The graviton's partner would be the gravitino. Think of the graviton as the messenger of the geometry of spacetime itself. The gravitino, then, would be a strange hybrid, a fermion that carries the force of gravity. It is a bridge between the quantum world of particles and the smooth fabric of general relativity. Theoretically, the gravitino would be incredibly massive, perhaps even at the scale of the Planck mass, which is a staggering 10 million billion times heavier than a proton. This immense weight is key to its potential role as dark matter. In many supersymmetric models, the lightest supersymmetric particle is stable, protected from decay by a quantum rule. If the gravitino is that lightest particle, it would be a perfect, stable relic from the Big Bang, floating through the universe as a natural candidate for the invisible mass-shaping galaxies. Yet the gravitino faces a serious and dramatic challenge from cosmology's earliest moments. The problem is not that it would be hard to find, but that it might have been too easy to make. In the extreme heat of the early universe, particles collided with unimaginable energy. Theories suggest that gravitinos could have been produced in enormous numbers during this period. If they were as heavy as suspected and produced in such abundance, their total mass density today would be far, far greater than what we observe as dark matter. They would have literally overclosed the universe, causing it to collapse back on itself long before stars ever formed. To avoid this, physicists must fine-tune the models, suggesting a later, cooler period of production or other mechanisms to suppress their numbers. But there is a second, even more precise test from the dawn of time: Big Bang nucleosynthesis. This is the process in the universe's first few minutes when protons and neutrons fuse to form the first light elements: hydrogen, helium, and a trace of lithium. The success of this process and the exact abundances we see today is one of the pillars of modern cosmology. It acts as a sensitive probe of conditions in that first cosmic furnace. If too many gravitinos were present and decaying during or just after this delicate window, they would have injected extra energy, altering the temperature and density. This would have changed the nuclear cooking recipe, resulting in elemental abundances that do not match what we observe in the oldest parts of the universe. The observed agreement between prediction and observation places extremely tight constraints on how many gravitinos could have been around, pushing them to the margins as a dominant dark matter candidate. So while the gravitino is an elegant idea born from a quest for a unified theory of everything, it struggles to fit the forensic evidence from our universe's birth. Its potential overproduction makes it a controversial figure, a theoretical marvel that the cosmos itself seems to have regulated very strictly. This tension between beautiful theory and hard cosmological data forces us to look for dark matter in places where the early universe gives its silent approval. Gravitinos are constrained by the universe's earliest chemistry, but another relic from that era is predicted by the very geometry of reality itself. It is a particle that should exist, a missing piece in the fundamental symmetry of the cosmos, the magnetic monopole. We are all familiar with magnets. Every bar magnet, from a simple fridge decoration to the Earth itself, has two inseparable poles, a north and a south. Cut one in half and you do not get isolated poles. You simply create two new, smaller magnets, each with its own north and south. This duality is baked into Maxwell's equations of electromagnetism. Yet, many physicists are convinced this is not the full story. They believe a single, isolated magnetic charge must exist somewhere in the universe. The reason lies in the quest for a grand unified theory, an attempt to describe all fundamental forces as one. In the extreme energies of the Big Bang, electromagnetism and the weak and strong nuclear forces were unified into a single, symmetric superforce. As the universe cooled, this symmetry broke and the forces we know froze out. Crucially, the mathematics of such symmetry breaking almost always predicts the formation of topological defects, stable knots in the fabric of spacetime. Think of it like freezing a pond. As water turns to ice, the process isn't perfectly uniform. Bubbles get trapped, cracks form, and the crystal structure develops imperfections. The magnetic monopole is one such cosmic defect, a stable, point-like knot where magnetic field lines converge or diverge from a single point, creating a particle with just one magnetic pole. These would not be ordinary particles. They would be monstrously heavy, perhaps 1,000,000 billion times the mass of a proton, making them potential candidates for super-heavy dark matter. Just a few drifting through a galaxy could exert significant gravitational pull. The hunt for them has been one of physics' great adventures spanning decades. Because they carry magnetic charge, a monopole moving through a loop of wire would induce a distinct electrical current, a clear signature. Experiments have used everything from ancient, pure iron ore deep underground to vast superconducting loops on the ocean floor, listening for that singular click. They have even searched for tracks in mica crystals, hoping to find evidence of a monopole that passed through the Earth eons ago. All have come up empty. This profound absence, known as the monopole problem, was a major motivation for the theory of cosmic inflation. The idea is that the infant universe underwent a period of hyper-fast expansion, stretching space-time so dramatically that it diluted any primordial monopoles to effectively zero in our observable patch of the cosmos. They might be out there, but so fantastically rare we may never find one. Yet their theoretical impact is immense. One wild proposal suggests that in the early universe, a flux of these cosmic monopoles could have acted as catalysts for proton decay. A proton is famously stable in our current universe, but grand unified theories predict it should eventually decay, just over timescales trillions of times longer than the current age of the universe. A passing monopole, with its immense energy and twisted fields, could have provided a shortcut, triggering protons to fall apart almost instantly in its vicinity. If true, this process could have helped shape the balance of matter we see today. So the magnetic monopole remains a ghost of prediction, a particle demanded by beautiful mathematics, whose very absence helped reshape our understanding of cosmic beginnings. The magnetic monopole is a defect frozen into the universe's fabric, but some hidden structures might be more fluid and alive. Enter the cue ball, a cosmic blob of pure field energy that could drift through galaxies as dark matter. Unlike particles, a cue ball is what physicists call a non-topological soliton. Imagine it not as a point, but as a bubble, a stable, extended object held together by its own self-interacting quantum fields. Think of it like a droplet of water where surface tension keeps it coherent, but here the forces are the abstract fields that govern particles themselves. Within supersymmetric theories, certain scalar fields, which assign a value to every point in space, could have settled into a low-energy state in the early universe. This state would prefer to clump together, forming vast, coherent regions of field. These are cue balls. Their stability comes from a conserved quantum number, often related to baryon or lepton number, the same properties that distinguish matter from antimatter. This charge is spread throughout the entire volume of the cue ball, locking it into a stable configuration that cannot easily decay. The result is a macroscopic object, potentially as massive as an asteroid, yet composed of no ordinary atoms. Its properties are utterly alien. Because it is a coherent field, a cue ball would interact with normal matter only through its immense gravity and perhaps the weak nuclear force, and even that interaction would be incredibly feeble. A cue ball the size of a football could pass straight through the Earth as if it were empty space, leaving no trace in our most sensitive detectors. Its journey would be silent and ghostly. Yet, these objects might leave a spectacular calling card. While stable, certain types of cue balls could eventually decay, especially if they encounter each other and annihilate. The energy release would be cataclysmic, converting their entire mass into a burst of ultra-high-energy particles. Some astrophysicists speculate that the mysterious ultra-high-energy cosmic rays we detect, particles with energies millions of times greater than anything produced in our largest colliders, could be the final sparks from dying cue balls in the distant galactic halo. These unexplained cosmic bullets arriving from the void with no clear source might be the death rattle of dark matter itself. So the search continues not just for particles, but for invisible, continent-sized fields wandering the dark, their potential demise written across the sky in streaks of impossible energy. While cue balls represent one form of dark matter as a macroscopic field, the early universe might have forged something even more extreme in the crucible of its own expansion. These are the WIMPs, particles so monstrously heavy they defy comprehension. Their name is not an exaggeration. Where a typical WIMP might have a mass around 100 times that of a proton, a WIMP could be 10 trillion times heavier or even more. At such scales, a single one of these particles would carry more mass than a whole bacterium, all packed into a point smaller than an atom. They are not merely heavy candidates for dark matter, they are the theoretical titans of the hidden cosmos. Their origin story is as dramatic as their mass. Ordinary WIMP are thought to be thermally produced, like steam condensing out of the hot bath of the Big Bang as it cooled. WIMPs could not form that way. They are born from the violence of cosmic inflation itself, that fleeting moment when the universe expanded faster than light. As this inflationary period ended, the immense energy stored in the inflattened field, the engine of expansion, was transferred into a firestorm of particle creation. In this chaotic transition, known as reheating, the gravitational field itself could have shaken loose ultra-massive particles directly from the fabric of spacetime. This process, called gravitational particle production, does not rely on thermal equilibrium. It is a raw act of creation where the geometry of the universe literally rips particle-antiparticle pairs out of the quantum vacuum. If conditions were just right, a stable, neutral particle of staggering mass could have been forged in this instant and survived to the present day as dark matter. Their incredible heft is both their defining feature and the reason they will never be found in an underground tank. A particle with a mass of 10 to the 16 giga-electron volts, a typical WIMP scale, would be utterly immovable. It would barely have any velocity, a slow drift through the cosmos known as cold dark matter in its purest form. More importantly, its interaction cross-section, the chance of it bumping into an atom in a detector, would be vanishingly small. You could line up a light year of our most sensitive xenon, and a WIMP would pass through it as if it were a ghost passing through a ghost. So if we cannot catch one directly, how do we hunt for such behemoths? The search turns to the sky, looking for the cosmological scars they might have left behind. Their gravitational influence in the early universe could have seeded the first structures, creating subtle differences in the clustering of galaxies we see today. Some models suggest that if WIMPs make up the dark matter, they could also be responsible for the supermassive black holes that sit at the hearts of galaxies, forming early seeds that grew over cosmic time. Perhaps the most tantalizing signature, however, comes from their potential demise. A stable WIMP is one possibility, but some theories allow them to decay, with lifetimes far exceeding the current age of the universe. The slow, rare decay of a WIMP would produce a cascade of ultra-high-energy particles, including gamma rays, neutrinos, and positrons. Our most powerful telescopes scan the diffuse gamma-ray background of the universe, looking for an unexplained excess at the highest energies that could be the faint, collective glow of dark matter titans quietly disintegrating across the cosmos. In this way, WIMPs represent a frontier of both mass and time, relics from the universe's first blink that may only reveal themselves through the grandest, most indirect echoes. From monstrously heavy singularities, we turn to a dark matter made of delicate, galaxy-spanning waves. This is the theory of fuzzy dark matter, a radical shift from thinking about particles to thinking about a coherent, rippling field. Here, the hidden component of the cosmos is not a discrete bullet but a fluid, a quantum wave on the largest scales imaginable. The candidate is often an ultralight boson, a cousin to the action but potentially billions of times lighter still. Imagine a particle so incredibly tiny in mass that its quantum nature, usually confined to the subatomic realm, becomes macroscopic. This is governed by the de Broglie wavelength, a fundamental quantum property that describes the wave-like character of any moving object. For a baseball, this wavelength is immeasurably small, but for an ultra-light boson moving slowly through a galaxy, this wavelength can stretch to an astonishing size, as large as an entire dwarf galaxy itself. This means the dark matter is not localized into point-like particles, but is instead a diffuse, interfering wave spread across vast volumes of space. The consequences for the architecture of the cosmos are profound. In standard cold dark matter models, heavy particles naturally clump together through gravity, forming dense halos and subhalos down to very small scales. Simulations predict that our Milky Way should be swarming with thousands of tiny satellite dwarf galaxies, yet we observe only a few dozen. This is known as the missing satellites problem. Furthermore, those dwarf galaxies we do see have those soft, cored centers rather than the dense cusps predicted. Fuzzy dark matter offers an elegant solution through wave mechanics. Picture the dark matter wave filling a galactic halo. Like any wave, it can experience interference. Waves that are in sync amplify each other, while waves out of sync cancel each other out. On scales smaller than its enormous wavelength, this interference creates a natural pressure that prevents the dark matter from collapsing into very dense, very small clumps. It smooths everything out. Think of trying to form a tiny, sharp sandcastle with wet, sloshing water. The fluidity resists forming that fine, peaked structure. In this wave-like picture, the very smallest dark matter subhalos, the ones that should host the missing satellite galaxies, are simply erased, washed out by quantum interference. Simultaneously, within the dwarf galaxies that do form, this same wave pressure prevents matter from piling up sharply at the center, naturally producing the soft cores astronomers observe. It is one elegant mechanism solving two major puzzles at once. The galactic core becomes not a point of maximum density, but a standing wave, a stable interference pattern at the heart of a galaxy. Visualizing this is key. Imagine dropping two pebbles into a still pond. The ripples spread out, and where they meet, they create a complex pattern of bright lines and dark nodes, areas of high and low wave intensity. Now scale that pond up to the size of a galaxy. The dark matter wave, shaped by its own gravity, would create a similar interference pattern across its volume, with the central core being one of those bright, high-intensity regions, but a broad and diffuse one, not a sharp spike. This is the proposed hidden skeleton of a dwarf galaxy, an invisible quantum wave pattern dictating where stars can gather and how they will move. The search for evidence is a challenge of cosmic proportions. Astronomers look for unique signatures in the way stars stream within dwarf galaxies, or for specific patterns in the faint, outermost stars of the Milky Way's halo, which would feel the gentle pressure of this wave like dark matter. It is a reminder that the universe's greatest secret may not be a thing, but a vibration, a single, fundamental note resonating through the emptiness, sculpting the galaxies we see from the shadows. The wave-like nature of fuzzy dark matter suggests a hidden fluidity to the cosmos, but what if the truth is not a fluid but a perfect reflection? Deep within the mathematics of symmetry lies a theory so elegant it proposes an entire shadow universe, a duplicate of our own, existing right alongside us. This is the idea of mirror matter. The principle is one of profound symmetry. Our universe is built on particles that obey a specific set of physical laws. Mirror theory asks a simple, radical question. What if those laws are not unique? What if there exists a perfect, hidden copy of all known forces and particles, a mirror sector that is identical in every way except for one crucial detail? It does not interact with our world through any of the known forces, not electromagnetism, not the strong force, not even the weak force. The only bridge between our universe and the mirror universe is gravity. They are two parallel realities woven together by the fabric of spacetime itself, yet completely invisible and intangible to one another. In this view, dark matter is not an exotic new particle. It is simply ordinary matter made of mirror protons, mirror electrons, and mirror photons, obeying mirror chemistry and mirror physics, all floating right through us. Every star in our sky could have a mirror twin, every planet a silent counterpart, their light and energy forever locked away in their own separate realm. The gravitational pull we attribute to dark matter halos would just be the collective weight of these mirror galaxies overlapping our own. The beauty of this idea is its naturalness. It does not require inventing new particles or forces from scratch. It simply doubles the cosmos, with the symmetry between the two sectors explaining why the dark matter abundance is roughly 5 times that of normal matter. It is a grand cosmic duplication, but if these two worlds are so perfectly separated, how could we ever find evidence for such a mirror? Scientists look for the most subtle of cracks in the wall between the sectors. One tantalizing hint comes from a persistent puzzle in particle physics: the lifetime of the neutron. A free neutron outside an atomic nucleus is unstable. It decays into a proton, an electron, and an anti-neutrino with an average lifetime of about 879 seconds. However, experiments measure this lifetime in 2 different ways. One method traps ultra-cold neutrons in a bottle and counts how many disappear over time. Another method uses a beam of neutrons and counts the protons produced from their decay. These 2 methods, performed with incredible precision, disagree by about 9 seconds. It is a small but statistically significant discrepancy that has lingered for years. Mirror matter offers a fascinating explanation. What if, very rarely, a neutron does not decay into our familiar particles, but instead oscillates into a mirror neutron? It would vanish from our detector entirely, seemingly decaying, but actually crossing over into the hidden sector. This would make the bottle-based measurement, which counts total disappearances, yield a shorter apparent lifetime, while the beam method, which counts only proton-producing decays, would be unaffected. That 9-second gap could be the time our neutrons spend, on average, briefly stepping into the mirror world before returning or staying there for good. The implications spiral out from there. If mirror matter exists and interacts only gravitationally, it could form its own complex structures. Mirror hydrogen could cool and collapse under its own gravity. Mirror nuclear fusion could ignite in mirror stars. These mirror stars would be completely dark to our telescopes, yet their immense gravity would bend the light from background galaxies, revealing themselves as gravitational lenses with no visible source. Some astronomers are actively searching the sky for these ghostly, lensing masses, potential evidence of entire celestial ecosystems we cannot see. And if mirror chemistry and biology are possible, the most mind-bending possibility of all emerges. In that parallel, invisible cosmos, mirror planets could orbit mirror stars, mirror water could flow, and mirror DNA could spiral. An entire shadow biosphere, a parallel tree of life, might have evolved in perfect silence alongside our own, forever separated by the thinnest, most impenetrable veil of physical law. We would share the same space, the same planets, even the same rooms, completely unaware of one another, bound together only by the mutual, silent pull of gravity. The search for mirror matter is a search for our universe's silent twin, a reflection in a cosmic glass we have not yet learned to see. Mirror matter proposes a hidden twin universe, but what if the extra space is not a parallel reality but a folded part of our own? The fabric of our cosmos might have more dimensions than we can perceive. This is the world of Kaluza-Klein particles, a concept that turns dark matter into a geometric echo. Our everyday experience is built on 3 dimensions of space and 1 of time. Yet, for over a century, theoretical physicists have played with a tantalizing idea: what if there are more? In the 1920s, mathematicians Theodore Kaluza and Oskar Klein proposed a radical model. They showed that if you wrote Einstein's equations of gravity in a universe with one tiny, curled-up extra-spatial dimension, the equations of electromagnetism emerged naturally. Gravity in 5 dimensions looked like gravity plus light in 4. It was a stunning unification, suggesting that the forces we know could just be the shadows of geometry in a higher dimensional space. The idea faded but never died, and today it lives on in modern string theory and models of universal extra dimensions. Here is the crucial insight: imagine a hosepipe. From a great distance, it looks like a simple one-dimensional line. But if you could shrink down to the size of an ant and crawl onto its surface, you would discover it is actually a 2-dimensional cylinder. The second dimension is curled up into a tiny circle, so small it is invisible to the naked eye. Now, replace the hosepipe with spacetime itself. Our familiar 4-dimensional universe could be like the long, extended part of the pipe. But there could be additional, microscopic dimensions curled up at every single point in space, far smaller than an atom. We are simply too big to move in those directions. We are stuck on the 4-dimensional brain of our existence. But subatomic particles are not. According to quantum mechanics, particles are also waves, and a wave can have a wavelength that fits perfectly around a curled-up dimension. Think of a guitar string. It can vibrate in its fundamental note, the lowest pitch, but also in higher harmonics, the overtones. A particle moving in a compact extra dimension behaves the same way. Its momentum in that hidden direction is quantized, meaning it can only take on specific, discrete values. To us, trapped in our 4-dimensional view, this single, higher dimensional particle does not appear as one entity. Instead, it manifests as an infinite series or tower of particles with different masses. This series is called a Kaluza-Klein tower. The lightest particle in the tower is the one with no momentum in the extra dimension, essentially standing still in that hidden direction. The next heaviest is the first harmonic, and so on. Each step up the tower corresponds to a higher energy and thus a greater mass. The lightest of these Kaluza-Klein particles could be absolutely stable, protected by a conservation law from decaying into ordinary matter. And if it is electrically neutral and only interacts very weakly, it becomes a perfect candidate for dark matter. Its origin is not a new field or a frozen defect, but a simple consequence of geometry, a particle that appears heavy and strange to us because we cannot see the full path it travels. In models of universal extra dimensions, all particles, not just gravity, can propagate into this higher dimensional bulk. This means there could be towers for electrons, quarks, and photons as well. The implications for detection are profound. If these extra dimensions exist, they could be explored not just by staring at the cosmos, but by smashing particles together with immense energy. When protons collide in a machine like the Large Hadron Collider, the tremendous energy could, in principle, be used to excite a particle into a higher Kaluza-Klein state. The signature would be dramatic and bizarre, a collision that seems to violate the conservation of energy and momentum from our 4-dimensional perspective. A certain amount of energy would simply disappear, carried off into the extra dimension by a particle that fled our brain. It would be as if you rolled a ball on a flat sheet and it suddenly vanished, its energy transferred into a direction you cannot point to. Alternatively, the lightest Kaluza-Klein particle, the dark matter candidate, could be produced in such collisions. It would escape the detector completely invisible, but its presence would be inferred by an imbalance in the energy and momentum of the visible debris. Scientists meticulously analyze collision events, looking for this exact kind of missing energy signature. So far, no definitive signal has emerged, but the search continues, pushing the energy frontier higher. The hunt for Kaluza-Klein particles is a hunt for the hidden architecture of reality itself, a search for the folded dimensions that might cage the dark universe and explain its most elusive inhabitants. Geometry gives us hidden particles, but a hidden universe might also have its own light. This is the theory of dark photons, the messengers of a secret force. In our familiar world, forces are carried by specific particles. The photon carries electromagnetism, the gluon carries the strong force, and the W and Z bosons carry the weak force. The dark matter hypothesis asks a compelling question. If there is a whole hidden sector of particles, could it have its own forces? And if so, would those forces have their own messengers? The dark photon is the prime candidate. It is theorized to be to a hidden, dark electromagnetic force what the ordinary photon is to our light. It would be the carrier of a dark electromagnetism, allowing dark particles to interact with each other, potentially forming dark atoms, dark chemistry, and dark stars within their own invisible realm. Yet, for this hidden cosmos to have any connection to ours, there must be a bridge. The most elegant possibility is a phenomenon called kinetic mixing. Imagine two separate oceans, one clear and one dyed dark, separated by a porous membrane. The membrane allows a tiny amount of water and thus dye to seep through. In physics terms, the dark photon could mix very slightly with our ordinary photon. This minuscule coupling would act as a portal, a forbidden channel between our world and the dark sector. It means that under the right conditions, a particle of our light could, with incredibly low probability, transform into a particle of dark light and vice versa. This tiny crack in the wall changes everything about how we might find dark matter. It provides a new production mechanism. In the high-energy collisions of a particle accelerator like the Large Hadron Collider, scientists could literally create dark sector particles by accident. A regular photon, energized by the smash of protons, could oscillate into a dark photon. That dark photon could then decay into pairs of dark matter particles, which would flee the detector unseen, leaving behind a signature of missing energy and momentum. Alternatively, the dark photon itself might decay back into familiar particles if it has the right mass, producing an unexpected bump in the data. A small excess of electron-positron pairs or muon pairs with a specific invariant mass. These are the bump hunts that physicists meticulously conduct, sifting through petabytes of collision data for a statistically significant spike that does not belong. Beyond colliders, the dark photon portal could explain lingering anomalies in other experiments. One of the most famous is the discrepancy in the measurement of the muon's magnetic moment, often called G-2. The muon, a heavier cousin of the electron, acts like a tiny spinning magnet. The strength of this magnetism is predicted by the standard model of particle physics with exquisite precision. Yet, experiments at Brookhaven and Fermilab have consistently measured a value that is slightly higher. This tiny deviation, just a few parts in a billion, could be the ghostly influence of virtual dark photons popping in and out of existence, subtly tweaking the muon spin. It is as if an unseen hand is gently pushing on the needle of the universe's most sensitive compass. To search for dark photons directly, experiments use a method of pure conversion. They fire a powerful beam of electrons at a fixed target. Most of the time, they produce ordinary photons or Bremsstrahlung radiation, but very rarely, an electron might emit a dark photon instead through that kinetic mixing portal. The dark photon, being weakly interacting, would fly through any shielding and then, meters downstream, could decay back into a visible electron-positron pair. Experiments like the Heavy Photon Search at Jefferson Lab are designed to catch exactly these events, using sensitive spectrometers to track the sudden appearance of pairs of particles from what seems like empty space. Other searches look for dark photons in the decays of exotic mesons, or even in the quiet depths of supernova explosions, where an excess of energy loss could signal particles escaping into the dark sector. The dark photon represents a thrilling shift in strategy. We are no longer just waiting for dark matter to bump into us. We are trying to shine a light into the void, hoping that something in the darkness might reflect a glimmer back. The dark photon offers a whisper of connection, but some theories embrace a profound and absolute silence. At the farthest extreme lies Planckian interacting dark matter. This is perhaps the most minimalistic idea of all, proposing a particle whose only meaningful interaction in the universe is gravity itself. Its defining property is a staggering mass set near the Planck scale. The Planck mass is a fundamental unit in physics derived from the constants of gravity, quantum mechanics, and the speed of light. It is about 10 to the 19 giga-electron volts, a number so large it is essentially the weight of a grain of dust packed into a volume a billion times smaller than a proton. A single one of these particles would be monstrously heavy, and according to this theory, that is all it is, a point of immense mass, deaf and blind to every other force. It would not feel electromagnetism, the strong force, or even the weak force. Its sole language is the curvature of space-time. This radical simplicity dictates its entire cosmic history. In the searing heat of the Big Bang, ordinary particles were constantly colliding and interacting, building the complex soup that led to our world. A Planckian dark matter particle could not be born from those fiery chemical reactions. Instead, it would have been forged through the most fundamental process imaginable, gravitational scattering. Even in that dense primordial plasma, two highly energetic particles could have come close enough that their gravitational attraction, normally negligible, became significant. That gravitational encounter could have ripped pairs of these ultra-heavy particles directly out of the quantum vacuum. They were not cooked in the thermal bath, but sculpted by the raw geometry of the universe itself. Once produced, their future was one of total isolation. They would drift through the expanding cosmos, indifferent to the formation of stars, the blast of supernova, or the birth of planets. They would pass through you, through the Earth, through entire galaxies, as if nothing were there, their presence felt only by the collective tug of their incredible mass. This purity makes them both a compelling idea and an impossible target for traditional searchers. No underground detector will ever flinch at its passage. No particle collider can muster enough energy to create one. Its detection is pushed entirely into the domain of gravitational phenomena and ancient relics. The primary hope for evidence lies in gravitational wave astronomy. If these Planck mass particles constitute the dark matter halo of a galaxy, they could occasionally collide and merge. The resulting gravitational wave signal would be unique, a chirp at frequencies much higher than those from stellar mass black holes, potentially within the range of future space-based observatories. More intriguingly, their gravitational influence in the very early universe could have acted as seeds for the densest regions of matter. Some models suggest clusters of these particles might have directly collapsed to form the very first black holes, the primordial black holes we discussed earlier. In this view, the hunt for ancient black holes is also a hunt for the fossilized remains of the universe's most aloof and massive constituents. Planckian dark matter represents the ultimate retreat into gravity's embrace, a hidden universe of silent titans whose only legacy is the shape of the void they silently bend. Silent titans sculpt the cosmos with gravity alone. But what if the dark sector is not a collection of solitary particles, but a bustling, complex society? This is the theory of composite dark matter, a hidden world as rich and structured as our own. Our visible universe is built from atoms, which are themselves built from quarks and gluons, bound together by the strong nuclear force or quantum chromodynamics. This force is responsible for nearly all the mass we see around us. Composite dark matter proposes that a perfect mirror of this process exists in the dark sector. There could be a hidden version of the strong force, a dark QCD, acting on a set of dark quarks and dark gluons we cannot see. Just as our quarks bind into protons and neutrons, these dark quarks could bind into dark protons and dark neutrons. And just as our protons and neutrons bind with electrons to form atoms, these dark nucleons could bind with dark electrons, governed by a dark electromagnetic force, to form entire dark atoms. The implications are staggering. We would not be looking for a single, boring particle, but for a whole hidden periodic table of dark elements. There could be dark hydrogen, dark helium, dark carbon, and molecules far more complex. This dark chemistry could unfold in complete isolation from our world, governed by its own laws but potentially just as intricate. The dark matter halos of galaxies would not be simple clouds of identical particles, but a dynamic mix of different dark elements, each with its own properties. Some might be light and fast, like dark hydrogen gas. Others could be heavy and slow, forming the dark matter equivalent of rocks or planets. This internal diversity could solve cosmological puzzles in elegant ways. For instance, the different components could interact with each other through their own dark forces, providing the self-interaction pressure needed to explain the soft cores of dwarf galaxies, much like the SIMP idea but with a ready-made mechanism. Furthermore, in the early universe, this dark nuclear physics could have led to dark acoustic oscillations. In our own history, ordinary matter and light were coupled in a hot plasma, creating pressure waves that left a specific imprint on the cosmic microwave background and seeded the large-scale structure of galaxies. A composite dark sector could have undergone its own version of this process. Dark photons and dark particles could have interacted, creating sound waves in the dark fluid. As the dark universe expanded and cooled, these waves would have frozen in, creating a subtle secondary pattern in the distribution of dark matter. This would then have gravitationally influenced the formation of the visible galaxies we see today. Astronomers could, in principle, detect this ghostly echo by studying the precise clustering of galaxies across billions of light years, looking for a signature that ordinary matter physics cannot explain. The search for such a complex dark sector pushes our experiments to their limits. If dark atoms exist, they might have a tiny, residual interaction with our world through the kinetic mixing of dark photons with our photons. This could allow a dark atom to very rarely scatter off an ordinary atom in a detector, not with a sharp bump, but with a more complex signature. Or in the high-energy collisions of the Large Hadron Collider, we might not produce a single dark matter particle, but a shower of dark particles, a jet of invisible debris that carries away energy and momentum in a specific pattern. The dream of composite dark matter is the dream of an entire shadow universe, not of silent ghosts, but of a hidden civilization of matter, following its own rules, building its own structures, and whispering its history to us only through the relentless, silent pull of gravity. That hidden civilization of dark atoms suggests a complex structure, but what if dark matter is not a solid or a gas, but a liquid that defies the very laws of friction? At the heart of some galaxies, the invisible majority might exist in a state of perfect flow, a cosmic superfluid. This is not just a fluid in the simple sense. A superfluid is a quantum phenomenon writ large, a substance that has lost all viscosity and can flow without any energy loss forever. To create one requires extreme cold and density. On Earth, we make superfluids by cooling liquid helium to a fraction of a degree above absolute zero. In the dense, cold cores of galactic halos, some theories propose dark matter could naturally condense into this exotic quantum state. Imagine the dark matter halo not as a static cloud, but as having two distinct phases. In the vast, sparse outer regions, individual dark matter particles drift like a thin, collisionless gas. This is the cold dark matter we know from cosmology. But as you move toward the galactic center, where the gravitational pull is stronger and the particles are packed more densely, a phase transition occurs. The particles overlap, their quantum waves synchronize, and they merge into a single, coherent quantum object, a superfluid lake at the galaxy's heart. This superfluid would have bizarre properties. It could creep up the sides of its own container, form persistent currents that never slow, and exhibit quantized vortices, tiny whirlpools where the fluid rotates in precise, discrete steps. But its most revolutionary feature might be its sound. In any fluid, vibrations travel as sound waves. In a superfluid, these quantum sound waves are called phonons. And here is where the theory makes a breathtaking connection. The phonons rippling through the galactic dark matter superfluid could produce an additional long-range force. This force would affect the motion of stars orbiting within the superfluid's region. Crucially, the mathematics of this phonon-mediated force can be designed to exactly reproduce the effects of a rival theory to dark matter, called modified Newtonian dynamics, or MND. MND proposes that there is no missing matter. Instead, Newton's laws of gravity break down at the very low accelerations found in the outskirts of galaxies. It has had remarkable success at fitting the rotation curves of many galaxies without invoking any invisible particles. For decades, dark matter and MND have been seen as irreconcilable enemies. Superfluid dark matter offers a stunning truce. On galactic scales within the superfluid core, the phonon force kicks in, providing the extra pull that makes stars orbit faster, mimicking MND predictions perfectly. But on the largest scales, the scale of galaxy clusters and the cosmic web, the dark matter is not dense enough to form a superfluid. There, it behaves like ordinary particle dark matter, clumping under gravity and providing the immense scaffolding needed to explain the universe's large-scale structure. In one framework, it bridges two warring paradigms. The superfluid's behavior elegantly addresses the same small-scale issues that plague standard cold dark matter, like the cusp core problem. A superfluid has a natural pressure that prevents it from collapsing into an infinitely dense point, automatically creating the soft cores observed in dwarf galaxies. Furthermore, the quantized vortices in the superfluid could act as gravitational seeds, around which normal matter might gather to form stars, offering a new link between the dark and visible worlds. The challenge, as always, is testing such an elegant idea. If galaxies have these superfluid cores, they might exhibit subtle differences in the orbital speeds of stars at very specific radii, a signature astronomers could search for with ever more precise galactic maps. The theory also predicts specific patterns in how galaxies align and interact within clusters, a ghostly fingerprint of the superfluid's quantum properties on a cosmic scale. It is a vision of dark matter not as a simple particle, but as a phase of matter, a cosmic condensate that reveals the quantum rules of the hidden universe in the silent rotation of a star. While superfluids propose a galactic-scale quantum state, some relics from the Big Bang never even joined the cosmic party. These are the elder or exceptionally light and decoupled relics, particles that have existed in a state of profound isolation since the beginning. Their story is the exact opposite of the WIMP. Remember, the classic WIMP is a social particle in the early universe, constantly colliding and interacting in the hot plasma. As the cosmos expanded and cooled, it suddenly found itself alone, freezing out of thermal contact. The elder never knew that social world at all. It was born on the outside, looking in. From its very creation, it was so incredibly weakly coupled to ordinary matter that it could never achieve thermal equilibrium. It never reached the same temperature as the rest of the universe. It was a spectator from the first instant. The production mechanism for these ghosts is called freeze-in. Picture a vast, crowded, and noisy banquet hall. This is the standard model plasma of the early universe. Particles are constantly bumping into each other, exchanging energy, reaching a shared, searing temperature. Now, imagine a silent, invisible observer standing just outside the door. Very occasionally, through a crack in the frame, a single morsel of food is passed out to them. They never enter the hall. They never mingle with the crowd. They simply collect these rare, handed-out particles one by one, slowly building up their own separate existence. That is freeze-in. Ordinary matter particles, through their incredibly rare and feeble interactions, very slowly produce elder. The process is so sluggish that it only becomes significant when the universe has already expanded and cooled considerably, meaning the final number of elder is fixed at a much later cosmic hour than the WIMP freeze-out. This origin defines their elusive nature. Because they were never in thermal contact, they are typically exceptionally light, potentially a fraction of an electron's mass, and exceptionally weakly coupled. Their interaction strength is many, many orders of magnitude fainter than even the feeble touch of a neutrino. This makes them arguably the most challenging dark matter candidates to detect directly. You cannot build a tank large enough to catch something that barely acknowledges our reality exists. So how do we hunt for a particle that never wanted to be found? The search turns to indirect and exquisitely precise methods. Since ELDR interact so weakly, they are almost perfectly stable, but almost is the key word. Over timescales far longer than the age of the universe, one might very rarely decay. The strategy, then, is to look for the faintest possible glow from these ultra-rare disintegrations across the cosmos. Astronomers scan the diffuse X-ray or gamma-ray background, the all-pervasive light that fills the universe, searching for an unexplained spectral line, a single, specific wavelength of light that has no other source. This would be the death rattle of a dark matter particle so shy we only see it in its final, vanishing moment. Other searches are even more subtle, looking for the minuscule gravitational influence a population of ELDR would have on the precise pattern of ripples in the cosmic microwave background, or for how they might slightly delay radio waves from distant pulsars. It is a hunt for whispers in a silent room that has been quiet for 13.8 billion years. The silent decay of a cosmic titan might seed the darkness with new life. This is the speculative theory that dark matter itself could be the final ash of an evaporating black hole. We have already met primordial black holes, those ancient relics from the Big Bang. Stephen Hawking's revolutionary insight showed that black holes are not truly eternal. They slowly lose mass, emitting a faint glow of particles now known as Hawking radiation. For a stellar mass black hole, this process is unimaginably slow, taking many times the current age of the universe. But a tiny, asteroid mass primordial black hole, forged in the first chaotic instant, would be reaching the end of its life about now. Its evaporation would not be a quiet fade. As a black hole shrinks, its temperature rises and the rate of radiation increases dramatically. In its final, furious moments, it would unleash a burst of high-energy particles. The question is, what remains when the fireworks are over? According to the standard picture, a black hole evaporates completely, leaving behind only a cloud of photons and other standard model particles. But some theorists propose a more intriguing possibility. What if the evaporation does not go to completion? Or what if, in those last quantum moments, the process creates something stable and new? The idea suggests that the evaporation of a primordial black hole could be the ultimate cosmic factory, producing a shower of stable, neutral particles that simply drift away into the void. These particles, born from the death scream of a black hole, would have no connection to the hot thermal bath of the early universe. They are non-thermal relics created cold and left to wander. Their properties would be dictated by the physics of the black hole's final instant and the unknown laws of quantum gravity. They could be incredibly light, like axions, or possess other unique signatures that make them perfect candidates for the dark matter we now detect only by its gravity. This creates a fascinating cosmic cycle. Primordial black holes, themselves potential dark matter candidates, could through their deaths give rise to a second, distinct form of dark matter, a phantom offspring. The observational hunt for this scenario is a search for echoes of these ancient explosions. One of the most promising places to look is in the gamma-ray background, the diffuse glow of high-energy light that fills the cosmos. If a significant population of primordial black holes evaporated in the relatively recent cosmic past, their collective final bursts would have left a distinct imprint on this background radiation. Astronomers meticulously analyze data from telescopes like the Fermi Gamma Ray Space Telescope, searching for an unexplained excess or a specific spectral shape that cannot be attributed to known astrophysical sources like pulsars or active galaxies. A faint, isotropic glow with the right energy signature could be the accumulated last flashes of a billion dying black holes. Another potential signature lies in the cosmic microwave background, the afterglow of the Big Bang itself. If these evaporation events happened earlier in cosmic history, the injected energy from the bursts could have subtly heated the intergalactic gas or altered the ionization state of the universe. This would create minute distortions in the perfect blackbody spectrum of the microwave background or affect how its light is polarized. Missions like the Planck satellite have measured this ancient light with exquisite precision, placing tight constraints on any such energetic injections in the first few 100 million years. So far, no clear signal has been found, but the search continues, refining our understanding of what the silence means. This theory ties together some of the most profound ideas in physics: the quantum death of black holes, the origin of dark matter, and the fossil light from the universe's infancy. It suggests that the invisible mass-shaping galaxies might be the final, cold remnant of a much more dramatic and violent genesis, a second-generation ghost born from the grave of the first. But what if the answer has been hiding in plain sight, made of the same ordinary stuff as you and me? For all our talk of exotic particles and hidden forces, we must confront a simpler, more stubborn possibility. Perhaps a significant portion of the dark matter is just regular matter that is extraordinarily difficult to see. This is the theory of baryonic dark matter, specifically in the form of cold, dense gas clouds drifting in the vast emptiness between stars. The building blocks of stars, planets, and life itself are baryons, the family of particles that includes protons and neutrons. For decades, cosmology has told us that baryons can only make up about 5% of the universe's total mass energy budget, with dark matter constituting over 5 times that amount. But could some of that dark matter actually be baryons we have simply missed? The leading candidate for this hidden ordinary matter is cold molecular hydrogen. Imagine vast, dark nebulae, not like the glowing stellar nurseries we see in telescopes, but colder, darker, and more diffuse. These would be clouds of hydrogen molecules, H2, with temperatures just a few degrees above absolute zero. They would emit almost no light of their own. No stars would be inside to heat them, and they would be too cold to glow in the infrared or radio wavelengths we typically use to map interstellar gas. They would be shadows within shadows. How could such enormous amounts of gas remain hidden? The primary method for detecting neutral hydrogen gas across the universe relies on a specific hyperfine transition, a tiny energy jump in the atom that emits a radio wave at a wavelength of 21 centimeters. But molecular hydrogen, where 2 atoms are bound together, does not have this convenient signature. It is virtually invisible at the temperatures and densities proposed for these dark halos. To find it, astronomers must rely on indirect and clever techniques. One method is to use the light of distant quasars, the brilliant cores of active galaxies, as cosmic flashlights. As this light travels billions of light years to reach us, it passes through the intervening space. If a cold cloud of molecular hydrogen lies in the path, it will absorb specific wavelengths of that quasar's light, creating dark lines in the spectrum. By surveying thousands of quasar sightlines, scientists can statistically map the distribution of this absorbing gas. Another powerful constraint comes from the cosmic microwave background. The early universe was a near-perfect blackbody, and its remnant glow today has an exquisitely smooth spectrum. If there were large amounts of cold, dense gas present at later times, it could have absorbed some of this background radiation and re-emitted it at a different temperature, creating subtle spectral distortions. The fact that we see no such distortions in the precise measurements from the Planck satellite places a severe upper limit on how much of this cold gas could exist. The consensus from these painstaking observations is clear. While there are certainly reservoirs of cold, diffuse gas in galactic halos and the cosmic web, they cannot account for more than a small fraction of the total dark matter budget. Perhaps 10 or 20% at most, the majority of the universe's missing mass remains stubbornly non-baryonic. This null result is in its own way a profound discovery. It forces us to abandon the hope that dark matter is merely ordinary matter hiding in the dark. The universe has played a trick on us, making the invisible majority not just difficult to see, but fundamentally different in kind from everything we are made of. The search must push further into the truly exotic. The universe's hidden inventory may not be a collection of particles, but a single, bizarre substance that changes its very nature over cosmic time. This is the theory of the Chaplain gas, an exotic fluid that promised to solve two mysteries with one breath. Its name comes from a Russian physicist who studied the aerodynamics of lifting surfaces, but its cosmological application is far stranger. The key lies in its equation of state, a mathematical description of how its pressure relates to its energy density. For most substances we know, this relationship is straightforward. For normal matter, pressure is negligible. For radiation, pressure is positive and significant. But the Chaplain gas has a negative pressure that behaves in a very specific, counterintuitive way. This unique property allows it to act like two completely different entities across the life of the cosmos. In the dense, early universe, this fluid would have behaved just like cold, pressureless dark matter. It would have clumped under gravity, providing the scaffolding for galaxies to form. But as the universe expanded and thinned out, its negative pressure would have begun to dominate. The fluid would have become more uniform, exerting a gentle, repulsive force that accelerates cosmic expansion. In this late time phase, it would act exactly like dark energy, the mysterious force driving the universe apart. For a time, this was a breathtakingly elegant idea. One single, continuous component could explain both the invisible mass holding galaxies together and the unseen energy tearing space itself apart. It was a unified dark sector, a cosmic chameleon that adapted its role to the needs of the epoch. The appeal was immense, offering a simpler, more parsimonious picture of the cosmos where two profound unknowns were revealed as two faces of the same entity. Yet, as with many elegant ideas, the universe provided data that did not cooperate. The first major conflict arose from the way galaxies cluster across the sky. Observations from massive surveys like the Sloan Digital Sky Survey map the three-dimensional distribution of millions of galaxies. This large-scale structure is a fossil record of how dark matter clumped over billions of years. A fluid that transitions from behaving like matter to behaving like a cosmological constant leaves a distinct signature in this clustering pattern. Specifically, it suppresses the growth of structure in a way that does not match what we observe. The universe we see has more galaxy clusters and a richer cosmic web than the Chaplain gas model can easily produce. Its transition into a smooth, dark energy phase happens too efficiently, preventing the formation of enough galactic structure to match reality. The second, more precise blow came from a subtle effect imprinted on the oldest light in the universe. This is the integrated Sachs-Wolf effect. As light from the cosmic microwave background travels for 13.8 billion years to reach us, it passes through the evolving gravitational wells of dark matter clusters. If the universe's expansion is accelerating due to dark energy, those gravitational wells are slowly weakening over time. A photon falling into a well gains energy, but as it climbs out, the well has become shallower, so it loses less energy than it gained. This results in a net boost to the photon's energy, creating very specific hotspots in the microwave background that are correlated with the distribution of matter in the nearby universe. The Chaplain gas model predicts a specific pattern for this effect that is stronger than what has been measured by satellites like Planck and WMAP. the observed correlation between the microwave background and the large-scale structure of galaxies is faint, almost negligible, which aligns perfectly with a simple cosmological constant but poses a serious challenge to the dynamic Chaplygin gas. Because of these persistent tensions with observational data, the model has largely fallen out of favor as a complete unified theory. It remains a fascinating footnote, a beautiful example of how physicists creatively tackle multiple problems at once, and a testament to how the hard evidence of the cosmos ultimately guides our understanding. The dream of a single dark fluid may have faded, but its legacy is the rigorous standard it set, proving that any theory must account for the intricate details written in the light of galaxies and the whisper of the primordial microwave sky. The elegant fluidity of a cosmic superfluid is not the only way to smooth out a galaxy's heart. Another compelling idea returns us to the realm of particles, but with a crucial twist: they talk to each other. This is self-interacting dark matter, or SIDM. While it sounds similar to SIMP, the focus here is not on a specific particle identity, but on a simple, powerful effect. What if dark matter particles, whatever they are, can occasionally scatter off one another like billiard balls in an invisible game? This single added rule within the hidden sector can reshape galaxies from the inside out. The motivation comes directly from two stubborn puzzles in our cosmic backyard. The first is the core cusp problem we have encountered before. Computer simulations that run the universe with standard, non-interacting cold dark matter consistently produce galaxies with sharply peaked central densities, a cusp of dark matter. Yet observations of faint dwarf galaxies show they have soft, flat cores. The second is called the too big to fail problem. The most massive dark matter subhalos predicted to orbit the Milky Way are so dense that they should easily form stars and become bright satellite galaxies. But we do not see them. The satellites we do see are far less dense, as if the most massive predicted subhalos simply failed to shine. They are too big to fail at galaxy formation, yet they appear to be missing. Self-interacting dark matter offers an elegant fix for both. When dark matter particles can scatter, they exchange energy and momentum. In the crowded center of a galaxy, where encounters are more frequent, this acts like a form of heat transfer. Just as air molecules in a heated room spread out to equalize temperature, self-interacting dark matter particles scatter from the hot, dense inner regions to the cooler outskirts. This process transports heat inward, which paradoxically pushes matter outward, eroding the sharp central cusp and replacing it with a gentle, constant density core. For the too big to fail satellites, the same principle applies. The most massive, dense subhalos would experience the most frequent scattering, efficiently transferring heat and lowering their central density. This makes them less extreme, bringing their predicted profiles in line with the faint, diffuse satellites we actually observe. It is a beautifully simple thermostat for the dark universe. But like any good theory, it must survive contact with reality on all scales. The strongest constraints come from watching what happens when galaxies collide. In colossal mergers of galaxy clusters, like the famous Bullet cluster, astronomers map the dark matter by its gravitational lensing. The dark matter from each cluster is found to sail right through the collision, clearly separated from the clumpy, slowed down ordinary gas. This proves dark matter is not strongly self-interacting on these vast scales. If it were, it would experience drag and lag behind, just as the gas does. The fact that it does not drag places a strict upper limit on how often these particles can scatter. The sweet spot for SIDM is a cross-section or likelihood of scattering that is just right. It must be strong enough to reshape small dwarf galaxies over billions of years, yet weak enough to allow dark matter in giant clusters to pass through itself like a ghost during a violent merger. Current astrophysical data suggests this is perfectly possible. There is a window where self-interactions are frequent enough to solve the small-scale puzzles, but rare enough to satisfy the large-scale cluster observations. This makes SIDM a robust and compelling framework, independent of the exact particle identity. It tells us that the dark sector may have a rich internal social life with rules that gently sculpt the visible structures we cherish. The silent majority is not just there, it is in constant, subtle conversation, and the shape of a galaxy is its lasting whisper. The thermostat of self-interaction is one way to smooth a galaxy's core, but the answer might lie in the very first motions of the hidden particles themselves. Our standard picture assumes cold dark matter, particles so heavy and slow they barely moved in the early universe, allowing them to clump together easily into the seeds of galaxies. But what if dark matter was born with a little more energy, a gentle warmth that kept it stirring just a bit longer? This is the theory of warm dark matter, a subtle shift with profound consequences. The leading candidate here is the sterile neutrino we met earlier, but with a specific mass in the kilo-electronvolt range. To understand the difference, think of two crowds trying to form a line in a strong wind. One crowd is made of heavy stones. When they stop moving, they stay exactly where they land, piling up into dense mounds. This is cold dark matter. The other crowd is made of dry leaves. They are lighter, and even after the wind dies, they skitter and drift for a while, resisting being packed into one spot. This is warm dark matter. A sterile neutrino with a mass of a few kilo-electronvolts would have been just like those leaves. In the first moments after the Big Bang, it would have streamed freely across the young cosmos with a significant thermal velocity. This streaming acts like a cosmic eraser on the smallest scales. Tiny density fluctuations, the seeds of future dwarf galaxies, get smeared out before they can grow. The result is a bottom-up universe with a missing bottom. Large-scale structures like galaxy clusters form just as we see them, but the very smallest dark matter clumps, the ones that should host hundreds of faint satellite galaxies around the Milky Way, simply never coalesce. This elegantly addresses the missing satellites problem without needing self-interaction or quantum pressure. The Milky Way's halo would be populated by fewer, more massive subhalos, which aligns much better with the few dozen satellites we actually observe, rather than the thousands predicted by the coldest models. So how do we search for a particle that smooths the cosmos by its ancient motion? One of the most promising methods listens for its death. If a sterile neutrino in the kilo-electronvolt range is dark matter, it should be unstable on timescales far longer than the age of the universe. But very, very rarely one could decay. The predicted decay channel is into an ordinary active neutrino and a photon. Because the sterile neutrino is so slow and massive, almost all its mass energy goes into that single photon. This creates a sharp, monochromatic emission line in the X-ray part of the spectrum. It would be a single, specific frequency of X-ray light, a pure tone ringing out from the dark matter halo of our galaxy and every other. For over a decade, astronomers have been scouring the sky for this elusive line. They point X-ray telescopes at regions of sky believed to be rich in dark matter but empty of conventional X-ray sources, like the centers of galaxy clusters or the diffuse halo of the Milky Way. In 2014, a tantalizing hint appeared. Researchers analyzing data from the XMM Newton Space Telescope reported a faint, unexplained X-ray line at an energy of 3.5 kilo-electronvolts, emanating from the Perseus galaxy cluster and several others. The excitement was palpable. It matched the predicted signature of a sterile neutrino with a mass of 7 kilo-electronvolts. Could this be the first direct signal of dark matter? The scientific community mobilized. Dozens of follow-up studies with other telescopes like Chandra and Suzaku aimed at the same clusters and at our own galactic center. Some saw a faint line, others saw nothing. The signal stubbornly refused to become conclusive. The latest analyses suggest it may have been a statistical fluctuation or the product of complex, poorly understood atomic physics within the hot cluster gas. The 3.5 kilo electronvolt line remains an unconfirmed ghost, a whisper that may have been just the wind, yet the search continues with renewed precision. Future missions, like the upcoming X-RISM Observatory, will have the spectral resolution to potentially distinguish a true dark matter decay line from astrophysical noise with definitive clarity. The hunt for warm dark matter is a hunt for a specific kind of silence, a universe where the smallest structures are absent, and for a single, pure note of X-ray light that could, at any moment, turn the cosmic background hum into a clear, defining song. The 3.5 kilo electronvolt line remains a spectral ghost, but another profound symmetry haunts the equations of the cosmos. Our very existence is a cosmic accident, a 1 in a billion fluke. For every particle of matter created in the Big Bang, an antiparticle should have been born as its perfect twin. When matter meets antimatter, they annihilate in a flash of pure energy. If the universe had been perfectly symmetric, every particle would have found its opposite, and everything would have vanished into radiation, leaving behind a sterile, empty void. Yet here we are, made of stars and planets and people. This means that in those first moments, an infinitesimal asymmetry must have occurred. For every billion antimatter particles, there were 1,000,001 matter particles. After the Great Annihilation, that 1 in a billion excess was all that remained to build our visible universe. This is the matter-antimatter asymmetry, and it is one of the deepest mysteries in physics. But what if that same story played out twice? This is the theory of asymmetric dark matter. It proposes a breathtaking parallel. The dark sector is not just a mirror, it might have its own version of that original cosmic crime. Perhaps dark matter particles also outnumbered their antiparticles by a tiny fraction in the early universe. After a similar period of annihilation, a stable relic of dark particles was left behind. And here is the elegant part. The similar abundances we observe today, with dark matter outweighing normal matter by roughly 5 to 1, might not be a coincidence. They could be a direct consequence of these two asymmetries being generated by the same underlying process, linked together in the furnace of the Big Bang. Imagine two buckets being filled from the same leaking tap. The tap represents some fundamental violation of symmetry in the laws of physics. One bucket catches the visible matter drips, the other catches the dark matter drips. Because they are fed from the same source, the amount of liquid in each bucket ends up being comparable, even if the buckets are different sizes. This solves the why 5 times more question with beautiful economy. The mechanisms for creating this linked asymmetry are as ingenious as they are complex. One leading idea involves a particle that acts as a messenger, decaying asymmetrically into both sectors. In the searing heat of the early universe, a heavy, unstable particle, perhaps predicted by grand unification, comes into existence. As it decays, it violates charge and parity symmetry, preferring to produce matter over antimatter. But instead of decaying only into quarks and leptons, it also decays into dark sector particles. The same physics that tipped the scales for us also tipped the scales for them, locking the two abundances together for all time. Another compelling possibility is that the two sectors were in thermal contact early on, sharing a common temperature, a process that generated an asymmetry in one, like the visible baryon asymmetry, could have been transferred or sequestered into the dark sector through high-energy interactions before the two worlds decoupled and went their separate ways. If dark matter is asymmetric, it carries a profound implication for its fundamental nature. It would mean that dark matter is not its own antiparticle. In particle physics, a particle that is its own antiparticle, like the photon, is known as a Majorana particle. But if there was an asymmetry, a survival of particles over antiparticles, then the dark matter particle must be different from its antiparticle. It is a Dirac particle with a distinct identity. This distinction is not just philosophical, it dictates how dark matter behaves in the modern cosmos. Most importantly, it means that annihilations are largely a thing of the past. In the standard WIMP scenario, dark matter is often its own antiparticle, and we hope to see it annihilating today in dense regions like the galactic center, producing gamma rays. But in the asymmetric model, the antiparticles were all wiped out in that primordial annihilation. The dark matter we have left is stable and lonely, with no opposite to annihilate with. The universe's dark inventory is a fossil of that ancient imbalance, a population of survivors with no one left to fight. This would explain why signals from dark matter annihilation have been so frustratingly faint. We are not looking at a bustling society of particles constantly colliding and sparking. We are looking at a graveyard of stable relics drifting in silent majority. Yet hope is not entirely lost. Even in an asymmetric scenario, there could be a small, residual population of dark antimatter, or the particles could have very rare, higher-order interactions that allow self-annihilation at a tiny rate. The search shifts from looking for bright annihilation fireworks to looking for more subtle effects, like the gravitational consequences of this asymmetric history on the first structures, or for the decay products of that long-vanished messenger particle in the precision data from particle colliders. Asymmetric dark matter weaves the fate of the visible and invisible worlds into a single, epic narrative of survival, suggesting that the reason we are here at all might be intrinsically linked to the reason the darkness has weight. The search for dark matter is often a hunt for something entirely new, but what if the answer is tied to a question we thought we had already solved? The discovery of the Higgs boson in 2012 was a monumental triumph, confirming the final piece of the standard model of particle physics. This mechanism, called electroweak symmetry breaking, is what gives particles their mass, but for decades before that discovery, theorists had explored other, more dramatic ways this cosmic weight-giving could occur. One of the most compelling alternatives was technicolor. In these models, the Higgs boson is not a fundamental particle. Instead, it is a composite object, a bound state of new, more fundamental particles called techni-quarks, held together by a new, powerful strong force analogous to the one that binds protons and neutrons. This techni-strong force would operate at a much higher energy scale, and its dynamics would naturally break electroweak symmetry without a fundamental Higgs field. Within this rich, hidden sector, a fascinating dark matter candidate emerges, the techni-baryon. Just as the ordinary strong force binds quarks into protons and neutrons, the techni-strong force would bind techni-quarks into stable, composite particles. The lightest of these techni-baryons, if it is electrically neutral and does not interact via the weak force, would be completely invisible to us except through gravity. It would be a heavy, complex object, a dark proton roaming the cosmos as a perfect candidate for the missing mass. The elegance lies in the connection. In this view, the mechanism that gives mass to the universe and the substance that shapes its galaxies are born from the same hidden strong dynamics. The Higgs and dark matter become two different manifestations of a single, deeper layer of reality. The discovery of a fundamental Higgs boson at the Large Hadron Collider made simple technicolor models less favored, as the particle scene closely matches the predictions of the standard model. But the idea did not die, it evolved. Composite Higgs models now incorporate a lighter Higgs that is still partly composite, a mix of fundamental and techni-quark ingredients. And within these more sophisticated frameworks, stable techni-baryons can still exist, their properties carefully tuned to avoid conflict with collider data while providing the correct dark matter abundance. Finding such an object would be a challenge of incredible subtlety. Because it is a composite state, its interactions with normal matter could be highly suppressed, but they might not be zero. If there is any portal, however tiny, between the techni sector and our own, these heavy techni-baryons could scatter off atomic nuclei with a signature distinct from a point like WIMP. Their composite nature might lead to a more complex recoil spectrum in underground detectors. Alternatively, if they can annihilate with their antiparticles, They could produce unusual patterns of cosmic rays or gamma rays, perhaps with features that reflect their internal structure. The legacy of Technicolor is a reminder that our greatest discoveries often close one door while quietly cracking open another. The Higgs boson we found may yet be a signpost pointing toward a vaster, more complex hidden sector where the forces that build mass also build the invisible architecture of the dark universe. Gravity's architects might not be particles but cosmic scars. When the universe cooled from its initial unified state, it may not have done so smoothly. Think of water freezing on a pond. As it crystallizes, the process isn't perfect. Bubbles get trapped and cracks form in the ice. In the same way, as the hot, symmetric plasma of the Big Bang cooled and settled into the distinct forces we know today, the transition could have created stable, persistent imperfections in the fabric of spacetime itself. These are topological defects, and they come in several terrifying forms. Cosmic walls would be two-dimensional sheets of concentrated energy, thinner than an atom but stretching across millions of light years. Monopoles, as we discussed, are point-like knots, but perhaps the most elegant and enduring candidate for a dark matter-like effect is the cosmic string. A cosmic string is not a string in the ordinary sense. It is a one-dimensional flaw, a rip in spacetime so dense that a single inch of it could weigh more than Mount Everest. It would be thinner than a proton, yet possess unimaginable tension, vibrating at near light speed. These strings would form a network, a tangled web left over from the early universe, stretching across the entire cosmos. Their gravitational influence is not from mass in the traditional sense, but from their sheer density. A string passing through a region of space would warp it profoundly. Imagine a taut guitar string laid across a rubber sheet. It creates a long, narrow valley of curvature. Any light or matter passing near a cosmic string would feel this distortion. This could create a remarkable optical illusion, double images of the same galaxy perfectly aligned with no lensing galaxy in between. It would be a ghostly gravitational lens, a signature of a line of pure tension slicing through the void. But could such a network actually account for the dark matter halos of galaxies? A dense enough tangle of strings, with loops and long filaments crisscrossing a galactic volume, could collectively generate the gravitational pull we attribute to particle dark matter. Their motion would stir the primordial gas, seeding density fluctuations that later collapsed into stars and galaxies. They would be the universe's original skeletons around which the visible cosmos was built. The most tantalizing evidence for these cosmic scars might be written in the oldest light we can see. As the universe transitioned through its early phases, the formation of a network of strings would have created gravitational waves, ripples in spacetime itself. These waves would have been imprinted on the cosmic microwave background, the afterglow of the Big Bang. They could create specific, faint patterns in the polarization of that ancient light, a swirling signature known as a B-mode polarization. While the primary source of such a signal is thought to be cosmic inflation, a component of it could be the faint hum from a network of vibrating cosmic strings. Scientists are meticulously analyzing data from telescopes like the BICEP array and the Planck satellite, searching for this specific fingerprint in the microwave sky. Finding it would not just reveal dark matter, it would open a window directly into the universe's first moments, showing us the cracks that formed as reality itself crystallized into the form we recognize today. Cosmic strings are scars from the universe's violent birth, but a deeper theory suggests the fabric of reality is woven from something far more fundamental. Beneath the level of particles beyond the forces, there might be nothing but tiny, vibrating loops of energy. This is string theory, and within its elegant mathematics lies a potential answer to the dark matter enigma. The core idea is radical yet simple. Every particle we know, the electron, the quark, the photon, is not a point but an unimaginably small, one-dimensional string. What makes an electron different from a photon is not its substance, but the way its string vibrates. Like different musical notes played on the same violin string, each distinct vibration pattern corresponds to a different particle with its own mass and charge. This beautiful unification comes with an astonishing requirement. For the math to work, these strings must vibrate in more than the 3 spatial dimensions we experience. They require extra dimensions curled up into intricate shapes at scales a billion times smaller than an atom. The geometry of these hidden dimensions dictates the possible vibrational notes and thus the entire particle content of our universe. This is where the hidden particles find their home. In the vast symphony of possible vibrations, there are countless stable, low-energy notes that do not correspond to any particle in the standard model. These could be the dark matter candidates we have been searching for all along. The lightest supersymmetric particle, the WIMP, could be one specific vibrational mode. A Kaluza-Klein particle could be a string vibrating with momentum in a curled-up dimension. An action could arise from the way certain fields wrap around the extra-dimensional geometry. In string theory, dark matter is not one mystery, but a near-infinite menu of possibilities. This leads to the infamous landscape problem. The mathematics of string theory does not predict one unique universe. It suggests a staggering multiverse of possibilities, perhaps 10 to the 500 different stable configurations, each with its own laws, forces, and particle zoo. Our universe, with its specific dark matter candidate, might just be one accidental bubble in a frothing cosmic ocean. This vastness is both a profound insight and a formidable challenge. How do we make a testable prediction when the theory allows for almost anything? The search becomes one of finding signatures that are generic to large classes of string theory models. One promising avenue is the existence of ultralight particles like axions or other moduli fields, which are almost unavoidable in string constructions. These could form the fuzzy dark matter that smooths out galactic cores. Another is the prediction of small, higher-dimensional black holes that could be produced in high-energy particle collisions, leaving a signature of missing energy as they evaporate into extra dimensions. Perhaps the most dramatic potential discovery would be evidence of the extra dimensions themselves. If the strings we are made of are not the only kind, and larger, heavier brains exist, our universe could be a 3-dimensional island floating in a higher-dimensional bulk. Dark matter might simply be ordinary matter trapped on a separate, parallel brane, forever close yet forever separate, its gravity bleeding through the dimensional divide. While string theory's complexity can seem daunting, its promise is a complete theory of everything where the question of dark matter is not an add-on, but woven into the very harmonics of reality. The silence in our detectors might be the quiet hum of a string vibrating in a shape we have not yet learned to hear. The universe's hidden strings vibrate in a symphony of possibilities, but one radical theory asks us to stop looking for new instruments altogether. What if dark matter is not a thing to be found, but a shadow cast by our own incomplete understanding of gravity? This is the paradigm-shattering idea behind emergent gravity, a concept that dissolves the need for any hidden particles by suggesting our most fundamental force is not fundamental at all. Instead, gravity might be an illusion, a side effect of a deeper reality, the storage and processing of information. The architect of this vision is theoretical physicist Eric Verland. His starting point is not galaxies or particles, but the nature of space itself. In Verland's framework, space is not a static stage. It is a dynamic, emergent structure woven from microscopic bits of quantum information. Think of it like the 3-dimensional image on a hologram. The rich, seemingly solid picture you see is not the reality. It is a projection from a 2-dimensional surface encoded with data. In the same way, our 3-dimensional universe, with all its forces and particles, could be a holographic projection from a lower dimensional boundary where information is stored. From this breathtaking premise, gravity emerges naturally, not as a fundamental force, but as an entropic force. Entropy is a measure of disorder, and it always increases. A classic example is the force you feel when stretching a rubber band. The resistance isn't a fundamental force of elasticity. It's because the polymer molecules in the band prefer a more disordered, tangled state. When you stretch it, you increase their order, and the system pushes back to maximize entropy. Verland proposes that gravity is exactly this kind of effect. When a massive object, like a star, sits in space, it changes the arrangement of the underlying information bits. It increases the entropy associated with that volume of space. When another object moves nearby, it feels a tendency to move toward the configuration of maximum disorder. This tendency is what we experience as gravitational attraction. It is not a force being exerted, but a statistical drift toward higher entropy. So where does dark matter fit into this informational cosmos? In Verland's theory, the extra gravitational pull we attribute to invisible particles is actually a consequence of ordinary matter's influence on this informational fabric. In the sparse outskirts of a galaxy where visible stars are few and far between, the emergent gravity equations predict an additional contribution to the gravitational field. This extra pull arises from the way the galaxy's total mass, including its visible core, modifies the entropy of the surrounding space. The mathematics of this effect can precisely reproduce the flat rotation curves of spiral galaxies without inserting a single dark matter particle. The dark matter halo is not a cloud of WIMP, it is a dark gravitational effect, an apparent force generated by the interplay of baryonic matter and the entropic nature of spacetime. This stands in stark opposition to the entire particle hunting enterprise. For decades, the strategy has been to find what is missing. Emergent gravity suggests nothing is missing at all. We have simply been misreading the cosmic ledger, attributing the books to an invisible accountant when the math was doing the work all along. The theory has scored some notable successes. It can naturally explain the tight correlation between the distribution of ordinary matter in a galaxy and its observed gravity, a link that is puzzling if dark matter is a separate, independent component. It also offers a fresh perspective on the universe's accelerating expansion, potentially linking dark energy to the same informational roots, yet formidable challenges remain. The most significant tests come from the collisions of galaxy clusters like the Bullet cluster. In these events, the gravitational lensing map, the apparent dark matter, is clearly separated from the visible gas. For particle dark matter, this is expected. The invisible clouds pass through each other while the gas collides and slows. For emergent gravity, where the effect is tied directly to the location of visible mass, this separation is deeply problematic. How can a gravitational effect be strongest where there is the least ordinary matter? Proponents argue that the equations of emergent gravity applied to the complex, dynamic environment of a collision might still account for the observations, but this remains an active and heated area of debate. Furthermore, the theory must still explain the detailed pattern of fluctuations in the cosmic microwave background and the large-scale structure of the cosmic web, which are exquisitely fit by the standard cold dark matter model. These are the hard benchmarks any new theory must meet. Emergent gravity is not yet a replacement for the dark matter paradigm, but it is a powerful and necessary provocation. It forces us to question our deepest assumptions. For a century, we have accepted that gravity is a fundamental force described by Einstein's geometry. What if that, too, is just a very good approximation of a deeper, more holographic truth? The hunt for particles continues in labs deep underground, but perhaps the real secret is that the universe is not hiding anything from us. We are just beginning to learn how to read the code from which it is made. The holographic universe of emergent gravity challenges our very conception of reality, but another profound puzzle is etched into the heart of every particle. This is the hierarchy problem, a mystery of cosmic proportions that may be intimately tied to the dark universe. It asks a deceptively simple question: why is gravity so unimaginably weak? The numbers are staggering. The force that holds you to the Earth is about 10 to the 40 times weaker than the electromagnetic force that binds atoms together. In the subatomic world, this weakness is expressed through the mass of the Higgs boson. The Higgs gives other particles their mass by interacting with them in a kind of cosmic molasses. But the Higgs itself has a mass, and according to quantum theory, this mass should be violently unstable. Virtual particles, constantly popping in and out of existence from the quantum foam, should be pushing the Higgs mass up to the highest energy scales, to something called the Planck mass, which is 1,000,000 billion times heavier than it actually is. It is as if a feather were resting on the seabed, resisting the crushing pressure of the entire ocean above it. Why does the Higgs remain so delicately light? This unnatural fine-tuning is the hierarchy problem, and it screams that our understanding is incomplete. The most compelling solutions to this puzzle all predict new physics, new particles, and often a perfect candidate for dark matter. Take supersymmetry. This elegant theory proposes that every known particle has a heavier, hidden twin. The magic is in the cancellation. For every virtual particle that pushes the Higgs mass up, its super-partner pushes it down by an equal and opposite amount. The result is a stable, light Higgs, and the hierarchy is saved. But this beautiful cancellation comes with a bounty of new particles. The lightest of these superpartners is often stable, neutral, and weakly interacting, a perfect WIMP. In this view, the hunt for dark matter is not a separate quest. It is a direct test of the mechanism that keeps the universe's fundamental masses in balance. If we find a WIMP, we may have also found the reason the Higgs is light, solving two monumental problems with one discovery. Another grand solution is the composite Higgs, where the Higgs is not a fundamental particle but a bound state of new constituents, like a proton made of quarks. In these technicolor or composite Higgs models, the Higgs is light because it is a pseudo-Goldstone boson, a particle arising from a broken symmetry, much like the pion in nuclear physics. These models also predict a zoo of new composite particles. Among them is often a stable composite state, a techni-baryon, that could account for the dark matter. Here, the dark matter particle and the Higgs are siblings, both emerging from the same hidden strong dynamics. Even the humble action, born to solve a different puzzle in the strong force, finds a role here. In some theories, the action's properties are linked to the same physics that stabilizes the Higgs mass, weaving the invisible particle into the very fabric that gives matter its substance. The connection is profound and inescapable. The same theoretical pressures that force us to invent new physics to protect the Higgs also populate the universe with hidden particles. Every time we look deeper into the quantum world to answer why things have the mass they do, we stumble into a universe teeming with potential dark matter candidates. This transforms the search from a hunt for missing mass into a forensic investigation of reality's deepest laws. The silence in our underground detectors is not just an absence of WIMP, it is data ruling out vast swaths of possible solutions to the hierarchy problem. The non-detection of supersymmetry at the Large Hadron Collider has already forced physicists to reconsider the simplest, most elegant models. Each null result sharpens the puzzle, telling us that if the answer lies in a hidden sector, it must be more clever, more subtle, or more bizarre than we ever anticipated. The dark matter we seek may be the key that unlocks not only the cosmos's hidden architecture, but also the secret of why the universe has the gentle, life-allowing weights that it does. The silence in our detectors may not be a failure, but a reflection of our own cosmic luck. Our final theory ventures beyond the universe we know, into the infinite and untestable realm of the multiverse. Here, the nature of dark matter is not a fundamental law, but a local environmental accident. Imagine a cosmic landscape of countless universes, each with different physical constants, different forces, and different particle zoos. In most of these universes, the numbers are wrong. Perhaps dark matter particles interact too strongly, smothering the formation of any structure. Maybe they are too weak, leaving gravity too feeble to pull together the first stars. In an endless sea of silent, empty, or chaotic cosmos, our universe is a rare island where the numbers lined up just right. The amount and type of dark matter we have created a specific gravitational scaffold, one that allows galaxies to form at the right pace, stars to burn for billions of years, and planets to coalesce in stable orbits. This is not a designed outcome, but a filtered one. We find ourselves here asking these questions precisely because this is the kind of universe that could produce beings capable of asking them. This idea is known as the anthropic principle. It is not an explanation in the traditional sense, but a shift in perspective. It suggests that the answer to why dark matter has the properties it does might be because if it didn't, we wouldn't be here to notice. From this viewpoint, the frustrating elusiveness of dark matter takes on a new character. Perhaps the particles are so weakly interacting not due to some profound symmetry, but simply because if they interacted any more strongly, they would have disrupted the delicate chemistry of the early universe, preventing the formation of the carbon in our bones. The specific ratio of dark matter to ordinary matter, that mysterious 5:1, might be a golden number for galaxy formation. Too much, and galaxies become too dense and chaotic. Too little, and they never properly form at all. This multiversal perspective is, by its very nature, nearly impossible to test. We cannot visit another universe to check its dark matter budget, yet it changes the philosophical ground beneath our feet. It transforms the search from a quest for a single, necessary truth to an investigation of what is possible within a narrow window of habitability. It asks us to consider whether the laws of physics are written in stone, or if they are more like the climate of a planet, just one possible arrangement in a vast cosmic archipelago. While it offers no direct path to a detection in a lab, it reframes every non-discovery. Each empty result from an underground tank, each ruled-out model, helps map the boundaries of that habitable window. It tells us what dark matter cannot be if life like us is to exist. So as we stare into the dark, we are not just looking for hidden particles. We are deciphering the unique signature of our own cosmic address, a message written in the negative space of reality, hinting at the unimaginable plurality of all that might have been and all that never could be. That silent pull from the darkness has ignited a universe of ideas, from the ghostly WIMP waiting in underground tanks to the galaxy-spanning waves of fuzzy dark matter, from the cosmic strings of a fractured infancy to the holographic whispers of emergent gravity. We have journeyed through 30 distinct visions of reality. Each theory is a testament to human creativity, a bold attempt to map the uncharted 95% of existence. Some propose solitary ghosts, others bustling hidden societies. Some seek answers in the geometry of extra dimensions, while others suggest we must rewrite the laws of gravity itself. This incredible diversity is not a sign of confusion, but of a science vibrantly alive, driven by a mystery that refuses to yield. The answer may very well lie within one of these 30 doors, patiently waiting for a single, decisive experiment to turn the key. Or, as history often warns us, the truth may be something entirely unforeseen, a concept so alien it has not yet even crossed the threshold of our imagination. The detectors remain silent, the telescopes scan, and the equations are refined, all fueled by a simple, profound need to know what holds our universe together. So we ask you, after this journey through the shadows, which vision resonates most? Do you find elegance in the minimalism of a Planckian titan, or does the complex society of composite dark matter fire your curiosity? Share your favorite theory in the comments below. This conversation is part of the search itself. And if you want to join more deep dives into the cosmos's greatest puzzles, be sure to subscribe. Look up at the night sky tonight. Every point of light is a clue, and the vast darkness between them is the question. Our story of the hidden particles is far from over. In many ways, with so many paths to explore, it has only just begun.